Congratulations on making it to the last day of the week. We've got a video here for you today. I'm going to introduce the last thing in probability that we'll talk about, and that is AND events. So we found simple probability, like the probability of rolling a 5 on a 6-sided die. We found the probability of OR events, the probability of rolling a prime number or an even number. Now we're going to find the probability of AND events. So what's the probability of rolling an even and a prime? All right. So these aren't any more difficult than OR events. I don't know whether that's a positive or a negative. Sometimes people really struggle with the OR events, and they find these just as hard. Sometimes people think the OR events are really easy, and they find these just as easy. It has the same dance beat, but we'll find the probability slightly different. I'll get into that detail here in a little bit. But just like with OR events, we ask ourselves a question before we ever decide what math to do. With OR events, we ask ourselves, is it mutually exclusive or not? Can they happen at the same time or not? Well, now we're going to ask ourselves, is it independent or dependent? An independent event is when, if the first thing happens, it does not change the probability of the second thing happening. Dependent events are the opposite. If the first thing does happen, it does change the probability of the second thing happening. And I know that's super confusing right now, but I just want to throw it out there first, and I'll get into more detail as we do these, and hopefully it clears itself up a little bit. All right, that just talks about the difference between independent and mutually exclusive. They don't mean the same thing. You can read that slide on your own time. I'm not going to read to you. All right, I'm going to shut my door here. My furnace just kicked on and decided to get cold again on us. All right. If you have independent events, you take the probability of the first one times the probability of the second one. When it was OR events, we just put a plus sign here. Well, with AND events, you multiply. Dependent events. There's something in here I know that looks really, really weird to you. It's this thing right here. All right, like it says right there, calm down, I'll explain what it is. But if the events are dependent, you take the probability of the first one times the probability of the second one, B, assuming the first one happened. Again, I know that's probably really confusing, but hang on, don't turn off the video, don't give up. It's probably a lot easier than you think. You just need to see some examples. So let's start to get into that. Okay, I have this slide up here for you to reference. I know that, especially this day and age, I don't think kids play card games quite as much. We used to play them all the time, but I think with the advent of technology and things, this is unfortunately kind of gone away. But every deck of cards has 4 suits, clubs, which look like the clovers. My dad calls them dog feet. They kind of look like dog prints. Diamonds, which big red truck here looks like a diamond. Hearts, which look like a heart, and spades, which kind of looks like a shovel spade, or an upside down heart with a stem in it. All right, so there's 4 suits, and every suit has an ace through king, and that's the order in which they go. So you might have to reference this if you're not really familiar with the deck of cards. If so, I guess you got a little bit of an advantage here. So we're going to draw 2 cards from the deck, and it says without replacement. So I'm going to draw 2 cards at the same time. I want to know what's the probability that I get a jack and the probability that I get a heart. Okay, so that's going to be the probability of a jack times the probability of a heart. If you look back at that slide, there are 4 jacks out of 52 cards. So the probability would be 4 out of 52. Now, you have to assume that this first event happened. So we did get the jack, okay? You assume that you got the jack. We did not put it back, so I no longer have 52 cards, I have 51 cards. So the probability changed. So these are dependent events. So this would actually be the probability of a heart given that we've already drawn a jack. There are 13 hearts, and now there are 51 cards remaining. Okay, reduce this down to 1 out of 13. Multiply 1, or no, we can reduce that, 1 and 1. So we get a 1 out of 51 chance. The probability of drawing 2 cards, one of them a jack, one of them a heart, is 1 out of 51. The probability that we draw a spade and a red card. Well, if I don't put the first card back, the probability of the second event is automatically going to change. Okay, on its own, the probability of getting a red card is half, 26 out of 52. But if I remove a spade from the deck, it's no longer 26 out of 52, it's 26 out of 51. So the first event happening caused the second event's probability to change. That's what it means to be dependent. So we have the probability of a spade times the probability of red given a spade. So that's going to be 13 out of 52 times 26 out of 51, because that, like I said, that spade's gone, so we only have 52 cards left. Okay, that reduces to 1 out of 4. 4 and 26, 2 goes into both of those. So it goes in twice, goes in 13 times. We get 13, and then 2 times 51, 102. So the probability is 13 out of 102. Okay, this time we're going to draw 2 cards, but we're going to replace. So in other words, we want to know the probability that the first time I get a queen and the second time I get a king. So that's going to be the probability of a queen times the probability of a king. If I draw that queen, that's a 4 out of 52 probability. The probability of a king is also 4 out of 52. If I draw the queen, put it back in the deck, it does not change the probability that I get a king. Right? The probability is exactly the same, so it doesn't matter if this happens or not. So these are independent events. So this is going to be 4 out of 52 times 4 out of 52. That reduces to 1/13. That reduces to 1/13, and we get 1 out of 169. So the probability would be 1 out of 169. Again, I'm going to draw a spade, and I'm going to put it back in the deck. So the probability of what I do here is not changed at all because I replaced the card. So that's going to be the probability of a spade times the probability of a red. That's 13 out of 52 times 26 out of 52. Okay, that's going to reduce to 1/4. That's going to reduce to 1/2. So the probability is 1 out of 8. So on the previous slide, we went the wrong way. We did not replace. So the probability of the second event got changed because we had one less card. So these were dependent. Here we did replace, so the probability stayed the same. These are independent. Okay, here I'm going to draw two cards from the deck. One time with replacement. So I want to know the probability that I draw an ace, put it back in the deck, and then draw another ace. Well, there are 4 aces. So I'm going to know the probability of an ace times the probability of an ace. The probability that I draw the first one is 4 out of 52. Put it back in the deck. So now there are 4 aces in the deck and 52 cards. The probability of the second one is not changed at all by the first one happening. So these are independent. And that's going to be 1 out of 13, 1 out of 13. It'll be 1 out of 169 again. Okay, the second time, I'm not going to replace. So these are going to be dependent events because the first time I draw an ace, I'm not going to put it back in the deck. So now I'm down to only 3 aces and 51 cards. So this would be the probability of an ace times the probability of an ace given you've already drawn an ace the first time. So that little vertical bar means the probability this happens assuming that this already happened the first time. So the probability that we get the first ace is 4 out of 52. I'm not going to put it back in the deck. So now we only have 3 aces left and we only have 51 cards left. So the probability we get an ace, given we've already got one the first time, is now 3 out of 51. This is going to reduce to 1/13. This is going to reduce to 1/17. And we get 1 out of, let me cheat here and use my calculator. (221). So the probability is 1 in 221 times. Oh, and this was a dependent event. Okay, let me erase this. Do another kind of example. We'll get away from cards here. We have a bowl, and in the bowl we have 9 red marbles, 4 blue marbles, and 3 white marbles. Marbles are drawn one at a time and replaced each time. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 red. 1, 2, 3, 4 blue, and 1, 2, 3 white. So 9 plus 4 is 13, plus 3 is 16. So we have 16 total marbles, 9 red, 4 blue, and 3 white. It says marbles are drawn one at a time and replaced. So you're going to reach into that bowl, see what marble you got, and then put it back in the bowl before you draw the second time. So the probability that we get a red one should be 9 out of 16. If I take that red one and put it back in the bowl, wouldn't the probability that I get a red one again be 9 out of 16? So if this happens, the probability of the second event does not change due to this happening. Therefore, these are independent events. All right, so both of these will be independent. So that's just going to be the probability of red times the probability of red. The first time, We draw a marble. The probability is 9 out of 16. Put it back. So there's still 9 red marbles, still 4 blue, still 3 white. So the probability that I get a red one here is also 9 out of 16. Multiply it across, we get 81 out of 256. Okay. If I draw a marble and put it back, the probability of the second event will not change. Okay. So this would be another independent event, probability of blue times probability of white. The probability that the first one we would get is blue, there are 4 of those out of 16 total. So that's 4 out of 16. I put that blue marble back, and the probability that I get a white one is 3 out of 16. So that would be 3 out of 16. This reduces to 1 out of 4. This doesn't reduce, so we get 3/64. So the probability that we get a blue one and a white one is 3 out of 64. Okay. The next slide, I do the exact same thing, but this time I don't replace. Right there, it emphasizes it, not replaced. So we still have 9 red, 4 blue, and 3 white. So we still have these marbles in the bowl. But this time, once I reach in and pick out a marble, I'm not putting it back in the bowl, I'm just going to put it in my pocket. So the probability of the second event will change if this event happens. Therefore, these are considered dependent events. Okay, so this first one, we would write it as the probability that we get a red times the probability we get a red given we got a red the first time. The probability that the first one is red, that is 9 out of 16. Now, that marble is gone. I'm not going to put it back in the bowl. So now our probability is going to change. That's why it's a dependent event. Now I only have 8 red marbles out of 15 total marbles. So that would be 8 out of 15. Okay, 8 and 16 reduce to 1 and 2. 3 goes into both of these, so that's going to reduce to 3 and 5. So we get 3/10. So the probability that you draw 2 red marbles without replacement is 3 out of 10. Okay. Now it's a brand new problem, so I'm going to put that red marble back. Now we want to know the probability that we draw a blue, don't replace it, and then draw a white. So that would be probability of blue times the probability of white given you already have a blue one. Well, the probability that the first one we draw is blue, there are 4 blue out of 16 total. So that's 4 out of 16 times, now blue one's gone. So now, instead of having 16 total marbles, we have 15. 9 plus 3 plus 3, that's 15. 3 of them are white out of 15 possible. That reduces to 1/4. That reduces to 1/5. So we get 1 out of 20. I know that's probably really confusing. All right. Highly, highly, highly encourage you to take advantage of office hours. Try to come in and ask questions. Okay. That's the last slide. So I think that was like slides 20 through 28, I think. No paper and pencil homework for tonight or for this virtual day. We'll pick up there next week and you'll have homework over this. Yep, that's all I got. All right, I hope you guys have a good weekend. Make sure you watch the video. If you're watching this in the morning, you have a Zoom meeting with me today. If it's periods 3 and 5, the meeting's at 12:30, and if it's periods 6 and 7, your meeting is at 1. I just want to check in, see how you guys are doing, give you a chance to ask questions, see how things are going, get a little bit of feedback from you. 10 to 15 minutes is all I'm asking for. Please attend if at all possible. Most of you should be able to make it. All right, have a good weekend. Bye.